All right, so today we're going to dive into what's called the chemistry mole or the chemistry mole concept. And no, it's not a mole that has beakers. Okay, so to kind of dive into it, we kind of want to look at what I call the mole man, the guy that discovered the chemistry mole. It's this guy right here. His name is Lorenzo Romano Amadeo Carlo Avogadro. Okay, he was an Italian physicist. He was the first to propose that at STP, equal volumes of gases had the same number of molecules. And what STP means is that standard temperature or pressure, which standard temperature is 0 degrees Celsius and standard pressure is 1 atm. This became what was known as Avogadro's law. Avogadro's law, he was able to use this principle to develop a relationship between the mass of elements and compounds and the number of particles that were associated with that particular mass. And with this, he called it what's called the mole. He was able to relate this via a number that he discovered, a constant that he discovered that was hereby known called as Avogadro's number. And the number is 6.02 times 10 to the 23rd particles per mole. So particles over moles is the actual unit for it. So the mole and mass. So we know average atomic mass. It's the average mass of all the associated isotopes for an element. We went into that in the second unit. And again, that's described in AMUs, which are atomic mass units. Again, carbon has an AMU of 12.01 AMU. Oxygen is 16.00. Formula mass is the sum of the average atomic masses of each element present within a particular chemical formula or compound or molecule in terms of AMU. So if I look at CO2, I have one carbon and I have two oxygens. So the way I would calculate its formula mass is I would say, okay, I have 1 times 12.01 AMUs, which is the average atomic mass for carbon. And since I have two oxygens, I'm going to take 2 times its average atomic mass for that element, and I add them together, so that means that CO2 has a formula mass of 44.01 AMUs. Same thing with water. Water is 2 hydrogens. Hydrogen is 1.01 AMUs, plus an oxygen, which is 16, and you get 18.02. Molar mass is the mass of 1 mole of an element or compound in the units of grams per moles. Okay, it's used to convert moles to the units of mass in chemistry mole problems. Just to identify, moles is enunciated as MOL. In the previous slide, I wrote MOLE just to make sure, but when you see moles as units, it's going to be MOL. So going back to mass versus weight, I know we touched on this concept in like the first unit, but we're just kind of go back over this just a little bit. Mass is the measurement of an object's inertia, okay, or the amount of matter that is in something. It is a fundamental property of all matter in the universe. Weight is the measurement of the force of gravity pulled on that mass, okay? So it's the weight of that force, the magnitude of that force pulling an object down. That's related to Newton's second law of F equals ma, so the force of gravity is equivalent to the mass times the acceleration of gravity. Again, A is equivalent to the acceleration of gravity. Chemistry measurements that we do, okay? Gram atomic weight is the weight of 1 mole of atoms of an element, okay? So it's the weight of 6.02 times 10 to the 23rd atoms of a particular element. It's equivalent to the atomic mass of the element, but in units of grams. So the average atomic mass of the element is equivalent to the gram atomic mass. It's just demonstrating that it's 1 mole of atoms per element. So we know that each hydrogen atom weighs 1.01 AMUs. But the gram atomic weight, the weight of 6.02 times 10 to the 23rd atoms of hydrogen is equivalent to 1.01 grams. Okay, so 1 mole of hydrogen is equivalent to 1.01 grams. Formula weight is the weight of 1 mole of a compound or molecule. So it's the addition of all the gram atomic weights of the elements within a particular formula that's presented to you. So again, sum of all the atomic masses or all the gram atomic weights present in a compound or molecule just in the units of grams. Okay, and then again, molar mass is the mass of 1 mole of a particular substance. So as long as the substance is the same, the molar mass of the substance will always be the same. Okay, so if you have pure oxygen, the molar mass of that is always going to be the same. If you have pure carbon dioxide, the molar mass of that is always going to be the same for that. But as soon as you change it, you know, if you turn carbon dioxide into carbon monoxide, then the molar mass of it changes as well. Okay, so chemical formulas in the moles. So chemical formulas can be related to the number of moles in the following way. The coefficients, which you've probably heard in math class, in front of the chemical formula within a chemical equation represents the number of moles of that particular substance, a molecule, an element, a compound, whatever. Okay, the subscripts that we've talked about plenty of times that identifies the number of elements within one molecule also can demonstrate the number of moles of that particular element within 1 mole of that substance. Okay, so for example, okay, I have 3 moles of glucose, okay, which means I have 3 moles of glucose. Within the 3 moles of glucose that I have, okay, for every 1 molecule of glucose, I have 6 atoms of carbon, 12 hydrogen atoms, and 6 atoms of oxygen. Okay, that's for 1 molecule of glucose. That's one single thing. Then, for every 1 mole of glucose, okay, I just times these atoms by the number of moles. So I'll have 6 moles of carbon for every 1 mole of glucose, 12 moles of hydrogen for every 1 mole of glucose, and then 6 moles of oxygen for every 1 mole of glucose. So for every 6.02 times 10 to the 23rd moles of atoms or molecules of glucose, okay, I'll have 12 times 6.02 times 10 to the 23rd atoms of hydrogen within that one particular mole or whatever. Okay, so again, just let that sink in for a second. Now, if I have 3 moles of glucose, then I take that coefficient. I know that this represents the number of moles for every 1 mole of glucose, the number of moles in carbon. So if I have 3 moles of glucose, then I can times these together. So I go 3 times 6. That means within 3 moles of glucose, I have 18 moles of carbon atoms. Then I have 3 times 12, 36 moles of hydrogen atoms. And then 3 times 6 here, which is oxygen, which is 18 moles. Okay. So this distinction between atoms or moles of something is dependent on what you are talking about. Do you have a glucose molecule that you're looking at individually, okay, and you're counting up the number of atoms there? Or do you have a pile of sugar that's a mole of glucose, and then you're trying to count up the amount of atoms that way? Okay, so it depends on exactly what you're looking at. If you're looking at an entire sample, you probably need to identify in the number of moles, which you can convert to the number of atoms later on. But you can't say that there's only 6 atoms within a huge pile of sugar. Like, that's not right. Okay, if you have 1 molecule of sugar, then yeah. But if you have a mole of sugar, then it's 6 moles of carbon or whatever. So calculating the molar mass. To determine this, we're going to just do an example. I want to break this step by step here for you. So I want to determine the mass of 10 moles of magnesium chloride, which is where bonding comes in. If you read magnesium chloride and you have no idea what that means, you need to go review your bonding like immediately, because this is where bonding starts to become very, very important. Okay, first thing you want to do is you want to determine the correct formula for the substance, because if you don't have the correct formula, your calculations are not going to make sense. Okay, so I know that the magnesium 2+ plus 2 chlorines forms MgCl2 because of the crisscross method. Okay, then I use the periodic table to identify the gram atomic weight for each element. Okay, now when it comes to gram atomic weights, you're always going to round to 2 decimal places. Always. Before you even do calculations, round the gram atomic weights to 2 decimal places. Okay, so if I look at the periodic table, you're going to see the average atomic mass as 24.31 AMUs. But remember, gram atomic weight is the same thing as the atomic mass, just in terms of grams per mole. Okay, so we're just putting that. So I have 1 magnesium, so it's 1 times that, and I get 24.31. I have 2 chlorines, so 35.45 is what you'll find on the periodic table. You do 2 times 35.45, and you get 70.90. That's grams per mole. Okay. Now, you add the gram atomic masses together to calculate the molar mass of that entire substance. Okay, so add them together. So what this is saying is that for every 1 mole of magnesium chloride that I have, there should be 95.21 grams of that substance. So for every 1 mole of molecules, or 1 mole of this compound, I should have a weight or a mass of 95.21 grams. Then you multiply the molar mass of the substance by the number of moles of the substance that's given in the problem. So I want to determine what the mass of 10 moles of this is. Well, I know that for every 1 mole, it's 95.21. So what I do is I take my 10 moles and I multiply it by my molar mass. And that's grams per mole. And then you get 952.1 grams of magnesium chloride. Now, how can I double check my answer? Well, I know that I'm trying to determine a mass, which means it needs to be in units of grams. Well, when I put this into my equations, I know that these moles are going to cancel out because there's one on top and one on bottom. What am I left with? I'm left with grams, and that's what I want. So if you have the right units, 99% of the time you're going to be right. Okay. So let's do another one. Let's determine the mass of carbon within 5 moles of sodium bicarbonate. So now we're identifying the mass of one particular element within the 5 moles of a huge substance. Excuse me. So we follow all the steps of the previous problem. We identify the proper chemical formula, so we know it's a sodium ion plus a bicarbonate polyatomic ion. Okay. Then I have to get the gram atomic weights for each individual element. I have 1 sodium times that. Hydrogen I only have 1 of. Carbon I only have 1 of, and I have oxygen of 3. So I multiply those all together and I get this total for each individual element. Then I add them up and I get the molar mass of sodium bicarbonate in general. Okay. Now the next thing you want to do is that you want to multiply the mass of the substance by the mass ratio of carbon to sodium bicarbonate. So what you do is you take the 5 moles of sodium bicarbonate that you're given in the problem, and then what you say is for the molar mass of sodium bicarbonate is grams per mole. Okay, so you get 84.02 grams of sodium bicarbonate over 1 mole of sodium bicarbonate, and that's going to cancel these moles out. Well, then you're left with grams of sodium bicarbonate, which is not what we want. Well, we know that for every 84.02 grams of sodium bicarbonate, which we have here, there's 12.01 grams of carbon in it too. So to cancel this out, this is going to cancel out, and you have 12.01 grams of carbon times the 5. So you'll have 60.05 grams of carbon. So again, double check your answers. Are you left with the units that you want? You want grams of carbon. Now, I know in the last couple of examples I haven't illustrated this, but when you're labeling your units, which you must do at all times, you need to label what elements you're talking about. Because as you can tell, if I have multiple grams in this problem, but if you don't label the compound or element that you're talking about, you're going to be confused on exactly where this stuff is going. And I've had students say, well, it's more busy work. But trust me, when you start doing it and you go to review, you're going to have a hard time figuring out where you got your numbers at. So you need to label your units with the particular element or compound or molecule that you're talking about. Trust me, it's good bookkeeping skills and it will help you. Now, there is another way you can attack this problem as well. We know from the chemical equation that for every 1 mole of sodium bicarbonate, okay, so the 1 coefficient here, there's only 1 mole of carbon that's present. Okay, and what this develops is what's called a molar ratio. You're going to hear me say this term a lot. So there's a 1-to-1 molar ratio between sodium bicarbonate and carbon itself. So what we can do is we can just multiply the number of moles of carbon to the 5 moles of sodium bicarbonate to calculate the gram atomic weight of what we have. So what we do is that we break this down. We say, okay, for every 5 moles of sodium bicarbonate, and there is 1 mole of sodium bicarbonate for every 1 mole of carbon. Okay, and that's from the chemical equation. Well, this is going to cancel these two out, but then I know that the gram atomic weight of carbon is 12.01 grams per 1 mole. So I know for every 1 mole of carbon that I have 12.01 grams of carbon. So what that's going to do is that's going to cancel these units out, and you're still left with grams of carbon, and you're still left with the same exact answer. So it's a little less weird of a calculation compared to this one. If this works for you, you can do that, but trust me, you're going to want to start using molar ratios, because as we dive further into other units, I'm going to be using this a lot because it's kind of a shortcut and it's what you really need to do. So just be aware you can attack the problem two different ways, but this is most of the time the easiest way because the key information is given in the chemical equation itself. All right, so that's the end of this video. If you have any questions on how those examples are performed, please come see me. We can break it down one by one together. If you feel like you need more practice, don't be afraid to shout up in class and tell me, hey, can we do an example of this? Or can we run through the example that was on the video? And so on and so forth. But please come talk to me or email me if you have any questions. Otherwise, thanks for watching this video, and I will see you in the next one, and see you in class.